The periodic table is one of the most used tools and resources in science, yet not a lot of people really understand why it is arranged the way it is. And today I'm hoping to give a broad and general overview of why the elements are arranged the way they are on the periodic table, and hopefully explain a couple of the trends that also go along with that. And I actually have a periodic table in my room, so hopefully this will kind of help to explain it. And first I'll be going over the general groups of the periodic table. So the first group we have is group 1, it's the alkali metals. Alkali metals are, of course, metals. They're like soft, they're shiny, they're very reactive, but the exception in this case would be hydrogen, because it's obviously a gas. And then moving on, we have group 2, which are the alkaline earth metals. They're similar to the alkali metals, except they're a little bit less reactive, and because they have 2 electrons occupying their outermost shell. We move down to group 3, which is the lanthanide series, and it's actually flipped horizontally on the periodic table instead of vertically here because it's too large to actually fit next to group 3. And right under are the actinide series. And the cool thing about the actinide series is that only thorium and uranium are naturally occurring on Earth, and every single element listed here in the actinide series is radioactive. And then moving back up to the main body, we have transition metals right here. And transition metals are metals that generally people know about. When we hear about a metal, we'll think about transition metal typically, because transition metals include metals like iron, cobalt, zinc, copper, gold, silver, and nickel, and metals like that. And these are metals that are typically used throughout common language and dialect throughout people's days. And so the cool thing about transition metals is that they're also very, very conductive. And this is typically what people use to transform into alloys and other different, and you can adjust their chemical properties and physical structures to make them more effective for different ways and different things. When we move across, we have more metalloids and post-transition metals, which aren't typically as important and as used, which is why I'm not actually going to go through them very specifically. But then we have this column up here with oxygen and carbon and nitrogen, and these are more of they're considered non-metals, but they're our organic compounds, is what you would see in organic chemistry very frequently. And of course we have the halogens, which is fluorine, chlorine, bromine, iodine, and so on and so forth, which are very, very reactive because they really, really want to get that extra electron to be stable. But they're typically seen making things like salts, like sodium chloride. So they're typically seen pairing with alkali metals like sodium. So that's our basic table salt. And then our last group here would be the noble gases, which is helium, neon, xenon, so on and so forth. And so they're all arranged in groups, of course, and each group has a specific family that they belong to for specific reasons. But that's not the only reason the elements are arranged the way they are in the periodic table. There are also a couple of trends, and actually there's probably 4 or 5 different trends, very, very significant trends that arise in the arrangement of the periodic table, but I'm only going to explain 2 of them, and the 2 that are, I suppose, the more easy to understand. They're pretty straightforward. So the first one is the atomic radius, and that's really just the size of your actual atom that you're dealing with your nucleus and your outer shells of electrons. And so the atomic radius actually will decrease across the periodic table and increase going down. And that's because going down is due to something called electron shielding, but going across is something that's kind of interesting, and it's that we are adding electrons and protons as you go across the periodic table. You're gaining protons and also gaining electrons. And one might think, well, wouldn't that make the atomic radius bigger because you're getting more stuff in there? That is the right way to think about it. But if you think that electrons are now increasing in quantity and so are protons, then the actual nucleus is getting smaller because the electrons and protons are getting closer and closer together. It's becoming more dense. and therefore the atomic radius is actually shrinking. It's becoming more charged dense in the middle. So that's why atomic radii actually decreases across the period. And something that arises because of that is electron affinity. And electron affinity is simply stated the electron's ability to accept the atom's ability to accept an electron. And so this parallels well with what I just described, because if an electron is on the outer shell and wants to actually bind or be accepted by the atom, then having a smaller atomic radius is going to help with that, because the distance between the electron and the proton is actually going to be smaller, and therefore easier for the atom to actually accept that electron. So the electron affinity will actually increase as you go across the periodic table as the atomic radius decreases. So a smaller atomic radius suggests an increased electron affinity. And these are just a couple of trends and ways to group the periodic table, but ultimately my hope is that it will bring more light and awareness to how you view the periodic table, instead of perhaps thinking that it is just a random arrangement and of elements, but there really is some beauty and sense to why elements are the way they are on the periodic table, and it's not just some random cause or case. So thank you.